Hello everyone and welcome to my stream. Today we're going to continue reading the Rust programming language book, and we are starting today with chapter 4, which is about ownership, which is one of the Rust's most unique features. So let's go ahead and see what we learn today. So let's see. Ownership is a set of rules that govern how a Rust program manages memory. Some languages have garbage collection. Other languages must explicitly allocate and free the memory. And Rust uses a third approach, which is that memory is managed through a system of ownership with a set of rules that the compiler checks. Yeah, so the borrow checker, right? Here it talks about the stack and the heap, for those that are not familiar with it. In the stack, you push the FIFO data structure, right? So first in is first out. And the heap is much less organized. You need to allocate data on the heap, so it's slower also. And you need to use pointers with the heap. So this indirection causes it to be slower also. Okay, so let's continue. Ownership rules. Let's see what are the rules. Each value in Rust has a variable that's called its own owner. There can only be one owner at a time, and when the owner goes out of scope, the value will be dropped. So, okay, pretty simple so far. We can only have one owner. So here we start with the interesting part, with the code. And they won't use a main function, so it will be more concise, but I'm going to create a new project for this chapter. And first, we declare a variable. It talks about the scope. So we declare an S variable. The variable is valid from the point which is declared until the end of the current scope. So if we open and close curly braces, we are creating a new scope. So, and the variable is not valid before we declare it. And after we declare it, it's valid, but once we close the scope, then we can no longer use S. So when S comes into scope, it's valid, and it remains valid until it goes out of scope, okay? Then the string type. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in the data types section of chapter 3. The types covered previously are all known size. Known size can be stored on the stack and popped off the stack when their size is over, and can be quickly and trivially copied and to make a new independent instance if another part of the code needs to use the same value in a different scope. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data. And the string type is a great example. So yeah, Now we're going to take a look at the string type, which allocates its data into the heap. Because so far we've only been using values that are stored on the stack. And that's not very interesting. So we already seen string literals, but a string literal is not the same as a proper string. For instance, string literals are immutable, and not every string can be known when we write our code, right? So if you want to take input from the user, we don't know how much space do we need to allocate, right? So the string manages data allocated on the heap and is able to store an amount of text that is unknown at compile time. And we can create a string like this using the from method. So let's go ahead and type it out. We declare a non-mutable variable of type string and initialize it with the hello string literal. So yeah, from is a method namespace from the string. And we will discuss more about this method syntax in chapter 5 and the namespacing in chapter 7. This kind of string can be mutated if we specify that it's mutable, and then we can push more content into the string, right? So we can append world, so we would have a hello world, and then if we print the string, we should be able to see the contents. So I run this, we indeed see hello world. Okay, so far so good. Now about memory and allocation. For string literals, we know the contents at compile time, so the text is hard-coded into the final executable, right? Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time. With the string type, in order to support mutable growable piece of text, we need to allocate an amount of memory on the heap unknown at compile time to hold the contents. This means memory must be requested from the memory allocator at runtime. We need a way of returning this memory, right? So like in C, we do malloc and free. We need something similar and equivalent in Rust. And in Rust, this is done automatically for us when we call string from. As I understand, memory will be allocated. Enough memory to hold the string that we pass in, the string literal. And then the part about deallocating, if we had a garbage collector language like C# or JavaScript, then we have this garbage collector that keeps running from time to time and looks for memory that is not being used anymore, and then it is in charge of cleaning up this memory. However, in Rust, we don't have a garbage collector, right? So we don't use a free like in C, but in Rust, the way it works is that memory is automatically returned once the variable that owns it goes out of scope. Okay, so we have here in the main this scope. So by the end of main, the string will be freed. And even if we were to open an extra scope here, Then if we wanted to use S here, we would not be able, right? Because at this point, the scope has been closed, so S has been freed already. And I can put so if I try to run this, I get an error. Cannot find value S in this scope. Okay, yeah. So this does not compile. And yeah, in C++, this pattern of deallocating at the end of the scope is called RAII. So, and the drop function in Rust will be familiar, would be the equivalent of the destructor in C++, right? So let's see other ways in which variables and data interact. And first we will see the move interaction. So multiple variables can interact with the same data in different ways in Rust. Let's look at an example of an integer. So if we declare an integer and then we assign another variable, this x variable, x will be 5 and then y will be also 5, right? So it makes a copy. We now have x and y and both are equal to 5. And this is because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Now let's look at the string version, okay? So if I have a string 1 and I assign it to a second variable s2, what will happen? Let me also to illustrate. So here they say that we would expect that the second line would make a copy of the value in S1 and bind it to S2, but this isn't quite what happens. Here we have a picture. So this is a representation of the string, right? We have a pointer to data on the heap, where we have the string data, hello in this case. Then we have a length of 5 and also a capacity of 5. This part, these three fields are stored on the stack, but this pointer points to the heap where the data is stored. The difference between length and capacity matters, but not in this context, so we can ignore it. And then if we make a copy from S1 to S2, we copy only the data from the stack, right? So we copy the same pointer, so we are pointing in the same heap location. We copy the length and the capacity. We don't copy the heap data, we just copy the pointer, right? This case is if we don't copy the data on the heap And this image is the case where we do copy the data on the heap, right? So in this case, all this heap data is also copied for S2. But it could be very expensive, right? If the string is very large, then we are copying a lot of data. And maybe we don't want that. Also, we said before that when a variable goes out of scope, Rust automatically calls the wrap function and cleans up the heap memory, right? So in the first image, we had 2 pointers pointing to the same location. So, and this can be a problem because when S2 and S1 go out of scope, they both will try to clean up the same memory on the heap. And that's bad. That's a double free. We really want to avoid this kind of issues. We can have memory corruption. So to ensure memory safety, after the line let S2 equals S1, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work, right? So here it's basically explaining what a move is, right? Here we are moving S1 into S2. So if we try to print S1 after we have moved it, we should get also an error. And let me delete this previous part so we don't get errors because of that. We get a few warnings, and here we get an error. Borrow of move valuable value S1. Move occurs because S1 has type string, which does not implement the copy trait. Value moved here, value borrowed here after move, right? So we are trying to borrow S1 and we have moved S1. So the compiler doesn't let us do that. If you heard shallow copy and deep copy, the concept of copying the pointer length and capacity with copying the data. Yeah, so the first image was describing a shallow copy where we only copy data on the stack but not data on the heap. And deep copy is where we also copy the entire heap data. But but Rust doesn't do a shallow copy when we reassign S1 into S2. It doesn't move, yeah. This solves our problem because only S2 is valid, so we won't do this double free, right? S1 is invalid, so it won't be freed. And then we have another way variables can interact, cloning. So if we have S1 again, and remember that here we are shadowing the previous S1. Well, in fact, let me delete. Here we are cloning S1. So I think in this case we are cloning the heap data as well. So in this case we are able to use both S1 and S2, and this should run. Yeah, S1 equals hello, S2 equals hello. In this case, the heap data gets copied, right? And this is explicit, so you see this clone in the code, so you are aware that this can potentially be expensive if you have a very large string. Stack only data copy. Yeah, so if we do the same as with strings, that remember that if this was a string, this was doing a move. Since integers are very simple and stored on the stack, this actually does a copy, so you can use both x and y here, right? Makes sense. And we don't need to call clone like here, because, yeah. And the reason for this is that integers have a known size at compile time and are stored on the stack, so the copies are quick to make. Yeah, probably they can even fit in a register in the CPU, so it's actually super fast. Rust has a special annotation called the copy trait that we can place on types that are stored on the stack, like integers. If a type implements the copy trait, a variable is still valid after assignment to another variable. And Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. I don't know what traits are exactly, but we will see probably in the following chapters. And basically, here it mentions that all the basic data types implement the copy trait. And even tuples if they only contain types that also implement copy, right? So now ownership and functions. What happens when we pass values to functions? Are they moved? Are they copied? And here it says that passing a variable to a function will move or copy, just as the assignment does. Okay. Okay. So if we have an is variable, and we pass it into a function, and we declare this function that it takes a string. We can print the string here. So, and yeah, and by the name, since this is doing a move, S is invalid here. We can no longer however, if we have a simple type that can be copied and we pass it into a function, yeah. here after the, yeah, it says here, after this scope is closed, the memory is freed and drop is called. But for an integer, it doesn't call drop and it doesn't have anything to free. So we should be able to still use s here, x here. Yeah, this compiles, we print hello, then we print 5 inside of the function, and then we print also 5 after the function has been called, right? However, if we try to print s here, we should get an error. Yeah. Value borrowed here after move. So the compiler doesn't allow us. Let's see now, return values and scope. Returning values can also transfer ownership. So we have a first function gives ownership, which creates a string and then returns the string to us. So yeah, here we are moving the string from the function to the caller. We also declare another variable s2, and we have another function which takes ownership of a string and then returns it, right? So we pass in a string and we just return it, we move it out. And finally here at the end of the main scope, S3 goes out of scope and is dropped, S2 was moved. Yeah, S2 was passed into here, so S2 is no longer valid. S1 goes out of scope and is dropped. So yeah, we drop S3 and S1, but not S2. Okay. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership with every function is a bit tedious. Yeah. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, right? So if we only want to print the string, and then we need to pass it in and return it if we want to still use it in main. Yeah, I can see why that is annoying. In addition to any data resulting from the body of the function that we might want to return as well. Yeah. That Rust does let us return multiple values using a tuple as shown in listing 5. Yeah, calculate length. So we pass in a string, but we also want to print the string later. So calculate length takes a string and it moves it. And then we compute the length of the string and we return the string and the length as a tuple. So then we can print it. So yeah, as this is very annoying, Rust has a method for improving upon this. So, and this feature is called references. Okay, so let's go to the next section. Yeah, so how do we fix this inconvenience of having to pass in the string and return it? We do that by using references, right? So if we want to use the string after calling a function, we can provide a reference to the string value. A reference is like a pointer in that its address we can follow, in that it's an address we can follow to access data stored at that address that is owned by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type. Here's how you would define and use a calculate length function that has a reference to an object as a parameter instead of taking ownership. So how to declare a reference? Right. So we create a string and then we call this calculate length and we pass it by using the ampersand sign. So yeah, we use the ampersand sign to create a string reference. And in the function signature, we also need to specify that we are taking now a string reference, right? Okay. And we only return the length now. And we can still use S1 because we only pass a reference into it. We are not passing ownership. Take a string, okay. So yeah, the representation of a reference is just some pointer pointing to another value. The opposite of referencing by using ampersand is dereferencing, which is accomplished with the dereference operator, right? Let's take a closer look. Yeah, we only get a reference, so it won't get dropped. Yeah, and also we need to specify it on the function signature. The action of creating a reference is called borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back. You don't own it, okay? What happens if we try to modify something we are borrowing? Try the code in listing 4.6. Spoiler alert, it doesn't work. So let's give it a shot. So if we declare a string yet again, and we call a function that changes it by passing a reference, something, and here we try to modify the string, string push set. This should not compile. Cannot borrow some string as mutable, as it is behind an ampersand reference. Help. Consider changing this to be a mutable reference. Yeah, so now they are going to explain to us how we can mutate a reference. So just as variables are immutable by default, so are references. We are not allowed to modify something we have a reference to, but we can have mutable references. With just a few small tweaks. So we need to declare S as mutable. Let's do that. We declare S as mutable, and then we also pass a mutable reference. And in the function, we specify that it's a mutable reference. So that will work, and it does work. Mutable reference have one big restriction. You can have only one mutable reference to a particular piece of data at a time. This code that attempts to create two mutable references to S will fail. So if we have one mutable reference to S and then another one, then this won't work, right? We get some warnings about unused. It's actually working. Because I missed the print statement. We need to actually use them. Yeah. Cannot borrow S as mutable more than once at a time. This error says that the code is invalid because we cannot borrow S as mutable more than once at a time. So we are allowed to mutate a reference, but we are only allowed to have one mutable reference at a time. And this restriction is what Rust what allows Rust to prevent data races at compile time. So a data race is the following. It can occur when two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data, and there is no synchronization, right? Yeah. So if more than one thread try to modify the same piece of data, and we don't have a mutex or something like that, then we can get a data race. Yeah. As always, we can use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. Yeah. So we can create a scope, create a mutable reference, and then when the scope goes out, we can create yet another mutable reference, and this should work. Rust enforces a similar rule for combining mutable and immutable reference. Yeah, we cannot. If you have a mutable reference, you cannot have non-mutable reference. It's exclusive, right? Yeah, because if we have a mutable reference, we can modify the value. But if you have an immutable reference, you expect that the value you are referring to won't get modified, right? The reference scope starts from where it is introduced and continues through the last time that the reference is used. For instance, this code will compile because the last usage of the immutable reference, the print line, occurs before the mutable reference is introduced. So here they are creating a mutable string, then creating two immutable references and printing them. And then R1 and R2 are not used after this point. So even though we don't have scopes, when we create the mutable reference, R1 and R2 are not being used anymore. So it's fine, no problem. Okay, I think I get it. The scopes of the immutable references R1 and R2 end after the print line. These scopes don't overlap, so this code is allowed. And this is called non-lexical lifetimes. Yeah, and borrowing errors can be frustrating. I've heard so much that the Rust borrow checker is a pain in the neck. So yeah, that's what they are saying here, but it's for the greater good, right? Dangling references. So in languages with pointers, it's easy to create a dangling pointer, which is a pointer that references a location in memory that has been given to someone else. So in Rust, by contrary, the compiler guarantees that reference will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. So here they are calling this dangle function, which returns a string reference. It allocates a string on the heap and has the S, and then we return just a reference to S. Reference to nothing. Yeah, because S is owned in the scope. When the scope goes out, it will get dropped. So the S reference will get invalidated. And this shouldn't work. And indeed it doesn't. So the error that we get, missing lifetime specifier. This function return type contains a borrowed value, but there is no value for it to be borrowed from. Consider using the static lifetime. Yeah. The error message is a bit confusing to me, but the point is that Rust doesn't allow this. Dangle returns a reference to a string. S is a new string. We return a reference to the string S, but here S goes out of scope and is dropped, so the memory goes away. So that's why Rust doesn't allow this. This is bad. Rust always prevents from having dangling references. And the solution here is to just return the string directly instead of a reference. That way ownership is moved out and nothing is deallocated. Okay. So to recap, the rules of reference are as follow. At any given time, you can have either one mutable reference or any number of immutable references, and references must always be valid. Okay. So next we'll look at different kinds of references, slices. The slice type. Slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. A slice is a kind of reference, so it does not have ownership. Here's a small programming problem. Write a function that takes a string and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. So let's follow along with this one. So we want a function that is called first word. It takes a string reference, and we return we don't know what. First for function has a string as parameter. We don't want ownership, so this is fine. But what should we return? we don't really have a way to talk about part of a string. However, we could return the index to the end of the word. Yeah. So we can return a number. And then we get the bytes from the string. And we iterate over the bytes. And if a particular byte is a space, we return the index of the space. Otherwise, we just return the entire length of the string. Yeah. Here they are using iterators, and we will discuss iterators in chapter 13. So for now, we can skip that part. Also, we are calling enumerate, which wraps the result of iter and returns each element as part of a tuple instead. The first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. So yes, I is the index of each byte of the string. An item is a reference to the byte. And then inside of the for loop, we search for the byte that represents the space by using the biliteral syntax. And if we find it, we return that location I. Otherwise, we return the length. So with this, we can use this function. In main, we can have a string s, and try to get the first word. And then we can clear the string. So word will be 5, which is the index of the space character of the string. And after getting the index, we clear the string, which is fine because here we just borrowed it. And after clearing, word still has the value 5, but there's no more string that we could use the 5 with. Okay. So because word isn't connected to the state of s at all, word still contains the value of 5. We could use that value 5 with the variable s to try to extract the first word out, but this would be a bug because the contents of s have changed since we saved 5 in word. Having to worry about the index in word getting out of sync with the data is tedious and error prone. Yeah, if we want to have another function to get the second word, we need two indices. One to indicate the start of the word and another to indicate the end or the length. So yeah, this is getting out of hand, and if we clear the string, then these indices, or you modify the string, these indices are no longer meaningful. So that's the reason Rust has string slices. And string slice is a reference to part of a string. And the syntax is by using the ampersand, and then in square brackets we put 2 indices. So 0 would be the starting index and 5 the ending index. 1 more than the last position of the slice. And internally, the slice stores the starting position and the length, which is ending index minus starting index. Right. We also have some extra syntax. If we start from 0, we can skip the 0. Yeah, I think Python has something similar. And also, if the slice includes the last byte of the string, we don't need to specify the last value here. We can just say from 3 to the end of the string. 0, 1, 2, 3. So this would be hello, I think. You can also drop both values to take a slice of the entire string. So we can either say from 0 to length or just dot dot. Okay, so now we are going to rewrite the first word function and return a string slice instead of an index. So yeah, let's do these changes as well. So now we return a string slice. We get the bytes the same, and instead of returning the index, we just return a string slice of s, starting at 0 and going up until I. And if we don't find any space, we just return the whole string as a slice. Now, let me also print the word here and try to run this. Word, hello, and it works. Okay. The value is made up of a reference. So this is much more useful, and in fact we can also print it after clearing the string. So even though, so we cannot do that because word is borrowing s. We cannot borrow s as mutable because it's also borrowed as immutable. So when we create the first word reference, this is an immutable reference, but in order to clear, we need a mutable reference, and we cannot have both at the same time, so we cannot do that. Yeah, and this is exactly what they are doing here. And this is because of the borrowing rules. We cannot have an immutable reference and also a mutable reference at the same time. And clear, since it's modifying the string, needs to be mutable. a mutable reference. So the Rust compiler does not allow this. String literals are slices. Recall that we talked about string literals. The type of S here is ampersand string. You can take slices of literals and string. So yeah, here it says that it is better to specify this as a string slice. Because if we try to try to call first word on a string literal like this, we know that string literals are slices, but here we only take a reference to a string, so this probably won't work. Expected struct string found struct. And here they are saying that we could use instead string reference, string slice. In that way it works. Okay. Yeah. Yeah, so instead of using a reference to a string, we can use a string slice. But how this is a string reference, there is some kind of conversion here. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of deref conversions. Yeah, so there is some kind of implicit conversion here. So if we specify a string slice, we can work with both string literals and references to string, which makes it more flexible, of course. But we will see this in chapter 15. Okay. And here we have a couple of examples how we can call this first word. We can pass a string slice of just a range of the my string. We can pass a string slice to the entire range. We can pass it just as a string reference, or we can pass, we can even pass a range of the string literal, or the entire string literal, okay? And we can have other kind of slices. Yeah, because string slice is just an example of a slice over characters. But if we have an array, we can also have a slice over the array, right? Yeah. The slice has the type ampersand I32. And it works the same way as string slices do, by storing a reference to the first element and the length. Okay. You'll use this kind of slices for all sorts of other collection. We'll discuss this in more detail in chapter 8. Okay, so that was quite a long chapter, very interesting. I think I'm going to need to experiment with this a little bit to get the hang of it. But yeah. And ownership is a fundamental part of Rust, right? One of the things that I hear more about Rust is the borrow checker. So yeah, in this chapter we got a first introduction to it. And then in chapter 5 we're going to look at grouping pieces of data together in structs. So yeah, so far we've only been using simple types, but in chapter 5 we're going to start looking how to create structs and how to use them. So yeah, but I will leave that for the next stream. Thank you so much for watching the stream, and I will see you all on the next one. Thanks for watching.